In this slide, we will talk about the trapezoidal rule, and in this trapezoidal rule, we will actually have a first order polynomial, linear polynomial. So we have this function again, which is difficult. Instead of that, we are using a linear polynomial, and this linear polynomial is represented by the function values of our range values a and b for integration. These, we know the function values, so the differentiation, the difference of them divided by the difference of the b and a, and x minus a. So this is very similar to, for example, the first order Taylor series. Simply we are representing this with a Taylor series, as you can see. That's that simple. But the order is linear, so we truncate after the first derivative. So in the truncation error, we will have the second derivative, and we showed that in the previous slide, but we will show them in the following slides as well. And the area under this straight line is an estimate of integral of fx between the limits a and b. So instead of taking this integral, we take this, and f1x becomes this function. So put it here. Take the integration of this. Basically, it becomes b minus a, fa plus fb divided by 2. You can check the book for the derivation of the trapezoidal rule from here to here, how to integrate. I'm not going to show that, and you are not responsible from the derivation, but you need to know about this only. So the integration is basically the summation of the two function values divided by 2 and b minus a. So this is the basic formulation for the trapezoidal rule to approximate the integral of a function. We can show a simple proof of trapezoidal rule using the graphical depiction of it. And the basic idea of the trapezoid actually is to get the area under this trapezoid, because we are the linear approximation or linear function gives us a trapezoid. As you can see here, when we have a trapezoid, the area of this is height times base 1 plus base 2 divided by 2. So when we have a function, we basically represent it with a linear function. And the concept is the same, but the trapezoid is on its side. So it's here, but bases are these, and the height is width here, just rotated 90 degrees, you can think of. So here what happens is width times average weight, that means height 1 plus height 2 divided by 2 is the area underneath. And when we have a function now, real function, we will have this integral limits a and b and the function values from the true function. Then we can get a linear approximation, and in this case we get the area underneath of a linear function by b minus a, which is the width here. This width is b minus a, and average height is this value, which is fb, and this value, which is fa. So plus sum them, fa plus fb divided by 2 is the average height. And using this formulation is the trapezoidal rule formulation that we showed in the previous slide as well. So this is the basic graphical depiction. You can simply have the idea using a trapezoid and area underneath. The error of the trapezoidal rule actually has the second order derivative and the third order error, as you can see here. And the reason of this is, we said 2 slides before that the trapezoidal rule formulation is similar to the Taylor series expansion, just truncated from after the first derivative. That means in the truncated part, the first derivative is the second derivative, actually, second order derivative. So this is the error, true error. And if you remember from Taylor series that to calculate this true error correctly, we have a psi value which lies somewhere in the interval from a to b, but we don't know the value of it. So if the function is linear, the result from the trapezoidal rule will be exact, like the Taylor series. For a first order function, the Taylor series can predict that first order function exactly, because the higher order derivatives are actually 0. So here, if we have a first order function that we want to approximate, the error has the second derivative, and the second derivative of it is 0. So the trapezoidal rule is linear and it will be exact integration. But if the function is a higher order with curvature, some error will occur, and that error is this actually. Let's show an example. We have this function which is in fifth order, and we want to use trapezoidal rule between a and b, which are 0 and 0.8. You can see the graph of the function. 0 is here and the function value is here. 0.8 is here and the function value is here. So when we want to have a linear function approximation, we combine these linearly. Then the area underneath here is the integral estimate. But the actual area is this. So if the order of the function is very large, like 5, the linear approximation can be very much different from the actual integration value. Here you can see we actually estimated a small area, but it is much more smaller than the actual integration area. So that means the area under the straight line here neglects a significant portion of the integral lying above the line. You can see here, this is the error, and you can calculate it using this function. In this slide, we have an example for the single application of trapezoidal rule for a function given here. This is the same function that we showed in the previous slide, with a fifth order function. And we want to take the integration between 0 and 0.8. And we know that the exact value of the integral is 1.640533. In reality, though, we are not able to integrate this. That's why we want to use trapezoidal rule. So we don't know this exact value. We just want to approximate it. So let's see how do we use the trapezoidal rule. First of all, let's remember the formulation of the trapezoidal rule. The integral is approximately equivalent to b minus a times fa plus fb and divided by 2. So in this scenario, we just need to know what b and a is, and these are here, and fa and fb are calculated by substituting these into the function and getting the fx results. When we do that, so let's write here, a is 0, then f0 from here, and we put 0 here, it becomes actually 0.2. Because all the terms are becoming 0, x's are 0, just 0.2. And let's now put b 0.8, then f 0.8. When you put this into the function, this becomes 0.232. So graphically you can see for 0 it's 0.2 here, 0.2, and for 0.8 it's actually a little bit higher, maybe this 0.232. That's why when we have a linear approximation using this, so there is a large error here. So that's why the integration will be very low, the area under this. Let's see. Let's put these into this function. Then I becomes about b minus a, 0.8 minus 0 times 0.2 plus 0.32232 divided by 2. Then I is equivalent to 0.1728 approximately. But we know that our actual integration gives this value, which is the area here, the total area, and it only gave us, with the approximation, very small portion of it. So we can calculate the error, ET. You know, this capital ET is calculated by subtracting the actual true error and the approximated error. And the result is 1.46773. And we can also approximate the percentage true error, which is just ET divided by true value, and that's 1.46773 divided by 1.4640533. This is the true value here, and the result is 89.5%. You can see there is a great amount of error, so it's too large. That's why only one single application of trapezoidal rule is not good for this function. The reason is basically it's a fifth order polynomial, and we are trying to predict its integral using a first order polynomial. That's a very large difference between the orders, so this error is large because of that. Let's check the approximate error in the following slide as well, using the truncation error formulation. For this example, we calculated a true error in the previous slide, but in real situations, we would have no foreknowledge of the true value. So we are not able to calculate a true error. Therefore, we need an approximate error. And for this purpose, we can use the error formulation for the trapezoidal rule, which uses the second derivative over the interval. And the formulation is basically this. We showed this in 2 slides before. Et is 1 divided by 12, the second derivative by Xi or psi b minus a, the third order. So here, the second derivative, we don't know this because we don't know this psi value. So we need to approximate this over the interval. How can we do it? We can use the mean formulation. Actually, f second order psi is equivalent to the integration between a and b fx dx divided by b minus a, but this fx is the second order function. So in this, we assume that we are able to take the derivative of the function. And remember that the function was in fifth order, so when we take second order derivative, it will be in third order. And let's remember the function here. So the function was 0.2 plus 25x minus 200 x squared plus 675 x cubed minus 900 x4 plus 400 x5. And if we take this derivative of it, we assume that we can take the derivative 25 minus 200, actually 400x plus 3 times 675 x squared minus 400 times 4x cubed plus 400 times 5x cubed, and we need second derivative in here. So take it, it's minus 400 plus 3 times 3 times 2 times 675, but it is actually 4050x minus 3 times 4 times 900, which becomes 10,800x squared plus 400 times 5 times 4, actually this is 4, then the result is 8,000 x cubed. So we will take the integration of this above here, put it here. Then what happens is we can take the approximation of this So let's show this way. This is an approximation. The approximation is shown by this way. This is mean function. This is mean. So this sign shows mean of the second derivative for x. So instead of using psi, we use x and mean of the derivative. So if we use this into here, then we have the approximate error. EA is equivalent to minus 1 divided by 12 again. Instead of f second derivative with psi, we use the mean value like this of the second derivative. This is second. And again b minus a cube. So this is our approximation error that we can use to approximate the true error. Basically, we are not able to calculate this. Instead, we will calculate this one. And for that, we need to calculate this, which is this actually. So this one is equivalent to approximately the mean value of x in the second derivative. And this is calculated by this formulation. Let's put everything here. It's integration between 0 and 0.8 b and a. And the second derivative is here. So write it here. Minus 400 plus 450x minus 1800 x squared plus 8000 x cube divided by b minus a, 0.8 minus 0. So this is the integration at the top, and at the bottom it's just the denomination, 0.8 minus this here. If you solve this, so we assume that we can take the integration of this, or you can again use trapezoidal rule here if you want to. For 0 and 0.8, just put the numbers here, get the results, then apply the trapezoidal rule. But here we assume that we can take the integration of this derived or second derivative function, and the result becomes minus 60. So this function value is minus 60. As we said, if we don't know how to take the integration of this, use the trapezoidal rule or use another approximation for taking integral. Similarly for this derivative, if you don't know how to take the derivative of this, use finite difference approximation, for instance, for the first and second derivatives, then use it in here. So basically you can use numerical methods here as well to get the derivative and this integration. So let's continue. Then let's use this formulation over here. EA is equivalent to 1 divided by 12, and the derivative is now minus 60. This one is this. Then times b minus a, 0.a minus 0, and cube. And from here, the approximate error is 2.56. And okay, we don't know the true error, but if we knew about it, the true error was actually, ET was, from the previous slide, we calculated it there, equal to 1.467733. So we assumed this error like 2.56. I mean, there is almost maybe 80% difference, but still these are in the same magnitude. So in between 1 and 10, let's say, that's the same magnitude and closer to 1 as well. That's why we can say we can approximate the true error in the same magnitude and sign also. So when we increase the degree of the numerical integration, like instead of trapezoidal rule, when we use second order, third order functions for integration, this error will be much less. So in this, because we have linear approximation, is this much high, the difference. And a discrepancy exists because the mean is not an accurate approximation of this one. It's just actually, we can show this way, it's just an approximation. And not very highly accurate approximation. And that's why we denote that the error is approximate by using the notation of EA. So be careful on that rather than using ET. If you don't know the true value, use EA. If you know the true value, use ET. And you can see we can approximate the error as well using this formulation here. And don't forget to take the mean like this with this formula to get the approximate derivative value.